of these are based on things that I've actually had to do to develop various exploits. For example, if one of the problems with heap exploitation is you don't know what the initial state of the heap is. You might have fragmentation on the heap. So remember in the beginning of the talk when I showed the initial Heap Feng Shui demo, we started with an empty heap, and then we allocated 2 blocks, and they were right next to each other. This is what you want. But if the heap contains holes, then allocating 2 blocks, when you allocate 2 blocks, they might actually go into the holes, and they might not be next to each other. So on the slide there, we have 2 holes, and our blocks are going to get there. And we don't want that. We want them to be next to each other. So to deal with that, we're going to defragment the heap, which can be accomplished by allocating a large number of blocks. It's pretty simple. You just do a loop. You allocate blocks of a certain size, and these blocks will fill out all of the holes, and then they'll fill out some more. And finally, the heap layout that we'll have at the end will be pretty much equivalent to a clean heap that doesn't have any allocations in it. Yes?
What if your block is bigger than the block? What if your block is bigger than
Now, usually when you deal with heap exploitation, you have a specific block size that you're interested in. For example, for this particular exploit, I needed 2 blocks that were 2010 in hex, of size 2010. And I needed these 2 blocks to be next to each other. So when I defragment the heap for this particular size, there might still be holes and fragmentation, but there will be smaller than 2010. And I don't care about those holes. I only care about the holes that are large enough to fit a 2010 byte chunk. So after this defragmentation, the next 2 allocations for this size are guaranteed to happen next to each other at the end of the heap. The next technique is for putting a block on the free list, and I think I mentioned this a few slides ago. The problem with the free list is that if you try to free a block, it will get coalesced with the free blocks around it, and when it gets coalesced, you'll have a free block of a different size, and it's pretty much unpredictable size because it depends on what the free blocks around it are. To deal with this, we're going to, if we want to put a block of a specific size on the free list, we're going to allocate 3 blocks, and then we're going to free the one in the middle. When we free it, we'll get a hole, but because the other 2 blocks next to it are allocated and we have not deleted the references to them, that free block in the middle cannot get coalesced. So we can use this to ensure that we have a block of an exact size on the free list. We can also manipulate the look-aside pretty easily to empty the look-aside. Remember that it's a singly linked list. It just has a certain number of blocks. It also has a limited capacity. So if we want to empty the look-aside for a certain size, like 512 bytes, you just need to allocate a bunch of these blocks. So we allocated 100 blocks of this size. The look-aside is empty. The first few blocks will come from the look-aside, depending on how many blocks there are on the list, and then after it's empty, we'll just keep allocating some more from the actual system heap, and then when this loop is done, the look-aside will be guaranteed to be empty. If we have an empty look-aside and we want to put something on it, we just need to empty it first, and then we're going to free a 512 byte block, and it's guaranteed to go on the look-aside because the look-aside is empty. We can use this to free 3. I was working on this exploit where the program was allocating, I think, 3 blocks of a certain size, and then the 4th block was the one that I had to control the contents of. It was an uninitialized memory bug. So what I did in that case was I freed the look-aside, and then I I emptied the leukocyte, and then I freed 4 blocks of that size. And the 4 blocks went on the leukocyte, so now we had a linked list of these 4 blocks. Then the application allocated the first 3, and when it got to the 4th one, it was the 4th block that I had just freed. So I had that level of control over what data the application would get. One of the cool things with the leukocyte is that you can use it if you're not dealing with an ASLR system. You can use it in a pretty neat way to exploit object pointer overrides without having to do any heap spraying very precisely. Remember that when you have objects, you have an object data structure. It points to the vtable, then the vtable points to the virtual functions. This sequence of pointers is very similar to the linked list that we actually have on the leukocyte. So what we can do is we can empty the leukocyte. We can build a fake vtable that contains just pointers to our shellcode, and then we can free that. When we free it, the head of the leukocyte linked list, I think I have a diagram here. So this is the fake vtable here that we freed to the leukocyte. This is the leukocyte head. It's just a pointer to the first entry in the leukocyte linked list. And the leukocyte head is in the default process heap. If you don't have ASLR, it will almost always be at a known location. In Internet Explorer, usually it's 150000. That's the base of the heap, and then you can add a fixed offset from that to get the leukocyte pointer. So we can use that as a fake object, and the first 4 bytes of it will point to the free block that we freed, which also serves as a fake vtable. The contents of this block will contain a virtual function pointer. In this case, if we're calling the virtual function at offset 8, that pointer, we're going to point it to a jump ECX trampoline, which we can find in any DLL or executable in our process space. And then if we have this code here, these assembly instructions for the virtual function, the address of the object will be an EAX, the address of the vtable will be an ECX. So when we execute the jump ECX instruction, we'll jump to the beginning of the free block. At the beginning of the free block, we'll have a null pointer because this is the end of the linked list on the leukocyte. These 4 null bytes will be executed as shellcode. They're equivalent to sub EAX AL. This instruction is guaranteed not to cause access violation or anything, because EAX points to our fake object, which is actually here, and we know this to be writable memory. Then we'll get to, after the null pointer, we'll get to data that we actually control, and we can put a jump there, and then we can have some shell code. So this method, we can get reliable shellcode execution with a fake object and a fake vtable without having to do any kind of heap spraying. We're basically reusing the leukocyte linked list to construct a fake object with a vtable. And I'm going to do a little demo of actually using this to exploit a vulnerability. All right. So this is an exploit for the MS06067 bug, which is it's the key frame vulnerability in one of the ActiveX objects. It's been patched. It was patched last year. But it's a pretty interesting vulnerability because the ActiveX object allocates a block, two blocks of a certain size, and they're initialized to 0. They're actually zeroed out when they're allocated. But then, because of an integer overflow, and these blocks are supposed to contain object pointers. They're basically arrays of object pointers. But they're normally initialized to 0. And the ActiveX object, when you trigger the vulnerability, due to an integer overflow, it will loop through these blocks, trying to call a virtual function on these pointers. The ones that are null, nothing will happen because it handles that case. But because of the integer overflow, the code will actually run off the end of the block that you've allocated into the data that's after that. And it will try to use that data as an object pointer. And it will try to call a virtual function through it. So if we control the object pointer that's there, we can use the technique that I just described to build a fake object and get shellcode execution. So I'm going to run the exploit. I have, just verify, I have my breakpoints set here. So we're going to get debugging output from the exploit. All right. So what happened here is you can see we did a lot of allocations for blocks of size 2010. This was to defragment the heap. After that, we needed to create 2 holes of size 2020. And we did this by allocating 5 blocks and then freeing the ones in the middle to make sure that they're not coalesced. And then you can see that here when we freed these blocks, we actually got these addresses like 930 and 68E0, which are right here. So you can see that they're in the middle of the 5 blocks that we allocated previously. Then we triggered the vulnerability. So all of these allocations actually come from the ActiveX object. So we don't have control over their order or sizes, but because we've set up the heap state in a particular way, we do have control over what memory these allocations will actually return. And the 2000C allocations are the ones that we care about. And we see that the blocks that get returned are the 2 blocks that we just freed above here. And we control the data in these blocks. One other thing to note is that the first 20C bytes of these allocations will be zeroed. But the data after that, between 20C and 2020, will be controlled by us. So when we trigger the integer overflow and the loop goes over the end of the block, it will reach the object pointers there, and we'll get shellcode execution. So, was there a question? No. I'm going to disable the breakpoints. I'm just going to let it continue, and we get this pop-up. And this pop-up is actually a message box call from the shellcode. So we got shellcode execution. So this is what you can accomplish with heaplib. To summarize, it gives you a very convenient API for manipulating the heap. You don't have to deal with any of the really low-level details. You still need to have a very good knowledge of how the heap actually works and what the results of your allocations and frees are going to be on the heap. But once you have that, you should be able to apply it